Welcome to Quantum, a channel dedicated to theoretical physics, with all its rigorous mathematical underpinnings and profound philosophical implications.
Today's lecture is structured into three main parts. First, prequantization via line bundle. We introduce the geometric framework that assigns quantum operators to classical observables using a complex line bundle with a connection whose curvature matches the symplectic form. Second, polarization. We refine the space of quantum states by selecting a polarization, a Lagrangian subbundle, which reduces the degrees of freedom and defines the physical Hilbert space. Third, metaplectic quantization. We address integration and operator issues by incorporating half-densities, ensuring a well-defined scalar product, and accounting for geometric corrections like divergence terms. Prequantization via line bundle. In geometric quantization, prequantization is the first step toward constructing a quantum theory from a classical one. It lays down a geometric framework where classical observables are promoted to differential operators acting on a complex line bundle over phase space. But unlike canonical quantization, which jumps directly to a Hilbert space, prequantization builds structure gradually, through bundles, connections, and curvature. We begin by defining a map from classical observables to operators. Each smooth function on phase space, say a function f, is associated to a differential operator p of f. This operator combines three elements: a derivative along the Hamiltonian flow generated by f, a geometric term involving the symplectic potential, and the function f itself. Together, they ensure that the commutator of two operators reflects the Poisson bracket of their classical counterparts. This satisfies Dirac's quantization condition, a foundational consistency check. However, the symplectic potential, the one form we denote theta, isn't uniquely defined. It can be shifted by the differential of any smooth function. This shift doesn't alter the physics, but it does alter the wave function by a local phase. The transformation looks like a gauge symmetry, a U1 rotation depending on position in phase space. Consequently, the correct setting for our wave functions isn't simply a space of functions, but rather sections of a complex line bundle, with local trivializations patched together using phase-valued transition functions. If the symplectic form is globally exact, then we can choose a global symplectic potential. In this case, the line bundle is trivial. It admits a global section, and wave functions can be written as ordinary complex-valued functions. The connection has a simple expression involving theta, and the geometry is straightforward. This trivial case gives us a clean laboratory to understand the basic structure of prequantization. Non-trivial bundles, local trivializations, and gauge transitions. But in general, omega may not be exact. Then the symplectic potential can't be defined globally. Instead, we work with local potentials on coordinate patches, and wave functions must be glued across overlaps using U1 transition functions, encoded by exponentials of smooth functions. This geometric setting reflects deeper topological properties of phase space. The line bundle becomes genuinely non-trivial, and wave functions must respect that topology. The connection on the line bundle is more than just a bookkeeping device. Its curvature is directly tied to the symplectic form. It must reproduce omega up to a constant factor involving Planck's constant. This condition isn't optional. It ensures that the geometric structure aligns with classical Hamiltonian mechanics. In fact, it guarantees that the lifted flow of any classical observable preserves both the Hermitian inner product and the connection, making prequantum evolution unitary and geometrically meaningful. Prequantum operator as lifted flow generator. When viewed geometrically, the operator P of f acts as the generator of a lifted automorphism on the total space of the line bundle. This automorphism mirrors the classical Hamiltonian flow on phase space, but it operates on quantum wave functions, preserving both the fiber structure and the Hermitian metric. In this way, each classical symmetry, when generated by a function f, becomes a quantum symmetry acting on sections of the bundle. What is a prequantization? So what do we need to prequantize a symplectic manifold? 3 ingredients: a complex Hermitian line bundle over the manifold, a compatible connection whose curvature is precisely the symplectic form divided by h bar, a Hilbert space of square integrable sections built using the volume form derived from the symplectic structure. This framework allows us to assign quantum operators to classical observables while keeping track of geometry, topology, and gauge symmetry. Geometry before quantum mechanics. Prequantization doesn't yet give us the final physical Hilbert space. The space of all square integrable sections is far too large. It includes too many unphysical states. To fix that, we need a polarization, a way to restrict to states that depend on only half the phase space variables, like positions but not momenta. But even before polarization, prequantization provides a remarkable bridge between classical symplectic geometry and the quantum world, one rooted in curvature, bundles, and flows. Polarization. In canonical quantum mechanics, a familiar starting point is the choice of a maximal set of commuting observables, for instance, the position operators. This defines a specific representation, such as the Schrödinger representation, where wave functions depend only on position, not momentum. Geometric quantization reformulates this process geometrically. Instead of choosing observables algebraically, we select a polarization, a smooth, involutive, Lagrangian subbundle of the tangent bundle of the symplectic manifold. This polarization identifies directions in phase space along which wave functions must be covariantly constant. The result? We reduce our wave functions from depending on all phase space coordinates to only half, precisely what's needed to build a quantum Hilbert space. More precisely, the wave functions are required to be covariantly constant along the directions defined by the polarization. This means, for every vector field in the polarization, the covariant derivative of the wave function vanishes. However, the connection on our prequantum line bundle has curvature, and that curvature is proportional to the symplectic form. Now, when we restrict the connection to the polarization directions, consistency requires that this restricted connection be flat. In other words, the curvature must vanish along those directions. This flatness condition imposes 2 important properties on the polarization. First, involution. The polarization must be closed under Lie brackets. This ensures that integral manifolds, or leaves, exist and form a foliation of phase space. Second, isotropy. The symplectic form must vanish when evaluated on any 2 vector fields within the polarization. If the polarization has half the rank of the full tangent space, these 2 conditions together mean that it is Lagrangian. So why do we impose these constraints? Because they allow us to restrict the prequantum Hilbert space to a smaller, physically meaningful subspace, one that depends only on the directions transverse to the polarization. These are the true quantum degrees of freedom. Effectively, wave functions become constant along the leaves of the foliation defined by the polarization and depend only on which leaf you're on, not where you are within the leaf. Mathematically, this means the wave function is defined on the space of leaves, not the full symplectic manifold. Let's see how this works in a concrete case. The cotangent bundle of a configuration space denoted T star Q. Here, the natural choice is the vertical polarization, defined by the directions along which only momentum varies. This polarization is spanned by vector fields tangent to the fibers of the cotangent bundle. In other words, partial derivatives with respect to momentum. If we require our wave functions to be covariantly constant along these directions, they must be independent of momentum and depend only on the configuration coordinates. This gives rise to the Schrödinger representation. Wave functions are functions of position. The leaves of the polarization are the fibers themselves. Each one is a cotangent space over a fixed configuration point. The space of leaves is therefore just the base manifold Q, and wave functions are naturally defined on Q alone. Beyond real polarizations, complexification. While real polarizations like the vertical one are elegant, they're also restrictive. On certain manifolds, such as the two-sphere, no global real polarization exists. This motivates a broader framework. We complexify the tangent bundle. A complex polarization is then a complex subbundle of the complexified tangent bundle, subject to the same conditions as before. It must be involutive, isotropic, and maximally so. This opens the door to polarizations on a much larger class of manifolds, including all Kähler manifolds, which play a central role in many quantum theories. Given a complex polarization, we can extract two real subbundles from it, one by intersecting the polarization with its complex conjugate, and another by taking their sum. These two bundles, often labeled D and E, carry important geometric meaning. D represents directions where the polarization is self-conjugate. It is, in a sense, the real part. E spans the full real distribution generated by the complex and conjugate complex directions. If the original complex polarization is integrable, so are these real distributions. Their leaf spaces, the quotient manifolds M over D and M over E, become important in defining the geometry of the quantum theory. To ensure a well-defined quantum theory, we want the leaf spaces M over D and M over E to be smooth and Hausdorff. If they are, the polarization is called strongly admissible. Two major classes of polarizations satisfy these criteria. Real polarizations, where the polarization equals its complex conjugate. In this case, the entire structure reduces to a foliation by real Lagrangian submanifolds, like in the Schrödinger representation. Kähler polarizations, where the intersection of the polarization with its conjugate is trivial. These polarizations are automatically strongly admissible, and they give rise to holomorphic representations, such as the Bargmann-Fock space for the harmonic oscillator. In sum, polarizations play a central role in geometric quantization. They determine which directions in phase space wave functions are allowed to vary, and which directions they must remain flat. By choosing a polarization, we carve out from the oversized prequantum Hilbert space a refined quantum state space, one that respects the geometry and topology of the classical phase space. This choice of polarization, whether real or complex, is the bridge between symplectic geometry and quantum representation theory. Metaplectic quantization. To perform geometric quantization, we begin with four key ingredients. First, a symplectic manifold, our classical phase space. Second, a prequantum line bundle with a connection whose curvature reproduces the symplectic form, scaled by Planck's constant. Third, a prequantum Hilbert space. This is the space of square integrable sections of the line bundle, measured using the Liouville volume form. And finally, a strongly admissible polarization, a choice of directions in phase space along which wave functions must be covariantly constant, reducing the number of independent variables in the quantum theory. This polarization must be complex, integrable, and Lagrangian. It also must allow for a well-defined inner product, and ideally admit a metaplectic structure, which ensures that half-forms can be defined globally. Step 1. Building the polarized Hilbert space. The first step in quantization is to restrict attention to polarized wave functions, those that are covariantly constant along the directions selected by the polarization. This defines a new Hilbert space, the polarized Hilbert space. But here's a challenge. In many cases, the space of such sections might be trivial or ill-behaved. This could happen due to topological obstructions or singularities in the foliation. To fix this, we refine the construction, either by tensoring with half-forms, allowing generalized sections, or using more advanced cohomological methods. Step 2. Promoting observables to quantum operators. Now comes the question, which classical observables can be promoted to quantum operators? In geometric quantization, the assignment is clear at the prequantum level. But this operator only acts correctly on the polarized Hilbert space if the observable's Hamiltonian flow preserves the polarization. In other words, if acting with the operator sends a polarized state to another polarized state. This leads us to a subalgebra of observables, the polarization-preserving ones. These are the functions whose associated Hamiltonian vector fields commute in a precise sense with the polarization. For such observables, quantization proceeds cleanly. We simply apply the prequantum operator and restrict it to the polarized space. In the case of vertical polarization, say on the cotangent bundle of configuration space, the polarization-preserving functions are those linear in momentum with coefficients depending on position. Their corresponding quantum operators include multiplication by functions of position and derivatives with respect to position, just like in Schrödinger quantum mechanics. For holomorphic polarizations, the structure is similar but formulated in complex coordinates, allowing a richer set of symmetries and observables. But not all physically important observables preserve the polarization. To handle this, we turn to the Blattner-Constant-Sternberg construction. Here's the idea. Even if the flow of an observable pushes us outside the polarized Hilbert space, we can track the flow, then project back to the original space. This projection, built using the inner product of the larger prequantum Hilbert space, defines a new operator. It extends quantization to observables beyond the polarization-preserving algebra. In certain special cases, like on flat spaces or Kähler manifolds, all polarizations are unitarily equivalent. Fourier and Bargmann transforms then implement the transitions explicitly. Step 3. Resolving the measure problem, half-densities. A major issue arises when we try to compute inner products between polarized wave functions. Because these wave functions are constant along the polarization leaves, integrating over the full phase space leads to divergences. We're essentially integrating constant functions over infinite directions. The solution is elegant. Instead of working with ordinary functions, we work with half-densities. These are square roots of volume forms. By tensoring the prequantum line bundle with a bundle of half-densities, we obtain sections that can be integrated naturally over the reduced base, usually the configuration space. This modification doesn't just fix the measure problem, it does so geometrically, with no need for arbitrary choices. Densities and divergence correction. There's one more twist. When quantum operators act on wave functions that include half-densities, an extra term arises. This is a correction involving the divergence of the classical Hamiltonian vector field. Physically, this correction ensures that the quantum operator is symmetric with respect to the inner product. Mathematically, it reflects how the volume element deforms under the flow. The result is a modified quantum operator, one that includes the classical observable, a derivative term, and a correction proportional to the divergence. This extra term can be viewed as a normal ordering adjustment, a familiar concept in quantum field theory. Closing summary. From geometry to quantum theory. In summary, the Hilbert space must be constructed using half-densities to resolve measure issues. Only a subset of observables preserve the polarization and are directly quantizable. Others require projection methods like BKS, and quantum operators gain correction terms from the geometry of the bundle and the flow of vector fields. This refined framework, called Metaplectic Quantization, ensures a consistent, geometrically grounded transition from classical mechanics to quantum theory. It's the final step in the core construction of geometric quantization. Thank you for watching. If you've enjoyed this journey through geometric quantization, make sure to like, share, and subscribe. Feel free to leave your thoughts or questions in the comments, and stay connected for more explorations in mathematical and theoretical physics.